Artificial intelligence looks weightless on a screen. Behind the screen, it is becoming one of the fastest growing new loads on the power system. The International Energy Agency estimates that data centers worldwide used about 485 terawatt-hours of electricity in 2025. Its central projection rises to roughly 950 terawatt-hours by 2030, with AI-focused facilities growing much faster than the rest. Those are estimates and scenarios, not a meter reading from the future. They also cover data centers broadly, not AI alone. But the direction is clear: the boom in models, agents, image generators, and cloud services is colliding with infrastructure that cannot be copied at software speed. A model can be duplicated in seconds. A substation, transmission line, power plant, or water system can take years. The world is not literally running out of electricity. The critical failure is more specific: in the places where AI companies want to build, enough reliable power may not arrive when they need it. Traditional computing facilities already consume substantial electricity, and not every data center is equally intensive. AI changes the profile because modern models rely on accelerators built to perform enormous numbers of matrix calculations in parallel. Thousands of GPUs can work together on one training run, exchanging data through high-speed links while drawing close to their rated power for long periods. The result is unusually dense demand, more computing packed into each rack, more heat concentrated in each room, and less tolerance for interrupted power. A conventional business server may spend much of its life lightly loaded. An AI cluster is expensive enough that operators try to keep it busy. Higher utilization improves the economics of the hardware, but it also keeps the electrical load high. Efficiency per calculation continues to improve, yet demand can still rise because models become larger, services reach more users, and cheaper computation creates new uses. Better chips do not automatically produce lower total consumption when the volume of computing expands faster than efficiency. Training and serving are different energy problems. Training is a bounded industrial job. A large cluster processes a huge dataset, adjusts model parameters, runs evaluations, and may repeat the cycle for weeks or months. The electricity is concentrated into a finite campaign, although experimentation and fail runs add overhead. Inference is what happens after deployment. Every prompt, search, image, translation, or agent action triggers computation to produce an answer. One request may be short, another may use a large model, long context, multiple tools, or repeated reasoning. That is why there is no single honest energy number for every AI request. At small scale, serving can look modest beside training. At global scale, millions or billions of daily requests accumulate continuously. Berkeley Labs' 2024 US model estimated that inference represented nearly 60% of AI server energy in 2023. While its scenarios had training overtake inference by 2028. The balance depends on model design, hardware, utilization, and user demand. The GPUs are only the visible core of the machine. CPUs prepare work. Memory feeds the accelerators. Storage holds models, checkpoints, logs, and datasets. Network switches move enormous streams of data between racks because an idle accelerator is wasted capital. Then the facility must remove the heat. Fans, pumps, chillers, cooling towers, or liquid cooling loops consume electricity, and some designs consume water through evaporation. Power also passes through transformers, switchgear, uninterruptible power supplies, batteries, and distribution equipment before reaching the chips. Each conversion loses a little energy. Backup generators and fuel systems stand ready because even a brief outage can interrupt expensive work or customer services. Berkeley Lab estimated that infrastructure outside the computing equipment accounted for about 30% of U.S. data center electricity in 2023, even after major efficiency gains. The exact share varies by climate, facility design, cooling method, and load. AI power demand is therefore not just the wattage printed on a GPU. It is the entire electrical and thermal system built around it. That system explains why data centers cluster in places. Developers look for large parcels of land, fiber routes, substations, transmission capacity, tax conditions, labor, and abundant electricity. Water availability can matter where evaporative cooling is used, while dry or liquid systems change the trade-offs rather than eliminating them. Proximity to users matters for latency, but access to power shapes the map. The U.S. Department of Energy has described connection requests for hyperscale sites in the 300 to 1,000 megawatt class, sometimes seeking service within 1 to 3 years. Utilities do not normally build generation, transmission, and transformers on that schedule. The concentration creates a paradox. A data center can be efficient because it operates at scale, yet its local impact can be enormous because demand arrives at one node on the grid. Berkeley Labs 2025 update projects U.S. data centers at 9.5 to 15.3% of national electricity use in 2030. That range is a scenario, not a confirmed outcome. A national percentage may look manageable while a county, utility territory, or transmission corridor faces a harder engineering problem. Cloud providers and AI companies are now competing not only for chips, but for megawatts, grid connections, transformers, and long-term generation contracts. Some sign power purchase agreements with wind and solar projects. Others seek direct arrangements with nuclear plants, geothermal developers, utilities, or new gas generation. Some propose on-site power so construction does not wait for a grid connection. These strategies can add supply, but they can also shift risk. Utilities may need to reserve capacity before a campus is fully built, while developers may request more power than they initially use. If projects are delayed or cancelled, customers can be left exposed to infrastructure built for demand that never arrived. If utilities underbuild, the data center waits and the AI service becomes more expensive. The IEA warns that the mismatch between fast-moving data center projects and slow-moving energy investment can raise costs in constrained systems, though predictable large loads can also improve asset utilization where surplus capacity exists. The outcome depends on planning, contracts, and who pays for upgrades. For surrounding communities, the argument is rarely just about technology. A new campus can bring construction work, tax revenue, and investment. It can also require new transmission lines, substations, gas pipelines, water infrastructure, or backup generators. Residents may ask whether household and small business rates will help finance upgrades for a private customer, whether diesel testing worsens local air pollution, or whether water use is compatible with drought planning. The answers vary by market and contract. Data centers do not automatically raise electricity prices, and they do not all use the same cooling system. But rapid, concentrated demand can create affordability and reliability risks when cost allocation is weak or generation arrives late. Transparency matters because announced capacity is not the same as operating load, and a campus may fill with servers over years. Regulators need realistic forecasts, enforceable interconnection terms, and protections against stranded investment. Without them, the race to host AI infrastructure can turn a private expansion plan into a public balance sheet problem. Clean solution. Wind and solar can be built relatively quickly and corporate contracts can finance new projects, but their output changes with weather and time of day. Batteries can smooth short peaks, support ride-through, and help data centers respond to grid stress, yet storage duration and cost limit how long it can replace firm generation. Natural gas can provide dispatchable power and may be built on site, but it adds carbon emissions, fuel price exposure, pipelines, turbines, and local air concerns. Nuclear power offers low-carbon, around-the-clock generation, but new projects face long development timelines, high capital costs, regulatory requirements, fuel constraints, and construction risk. Existing plants are finite assets, not an unlimited pool waiting for data centers. The IEA expects renewables to supply nearly half of the growth in global data center electricity demand through 2030, with natural gas also playing a major near-term role and nuclear growing later. That is a projection, and the mix will differ sharply by region. Even a renewable energy agreement needs careful interpretation. A company can contract for enough wind or solar generation over a year to match its annual consumption while the data center still draws from the local grid every hour. At night, during calm weather, or when transmission is constrained, the physical electricity may come from gas, coal, nuclear, hydro, storage, or imports. Hourly matching and additional clean generation are stronger tests than annual accounting, but they are harder and more expensive. Meanwhile, the environmental footprint extends beyond electricity. Cooling can consume water, fossil generation emits carbon, and rapid hardware replacement carries mining, manufacturing, and electronic waste burdens. If power, transformers, turbines, permits, or water become scarce, new campuses will take longer and financing costs will rise. Those costs can flow into AI subscriptions, cloud prices, and limits on free services. The decisive constraint may not be whether engineers can design a larger model. It may be whether society can build the physical systems to power it, cool it, connect it, and justify the trade-offs.